Every single day, billions of people hold something so ordinary, they never stop to question it. A drinking glass, a phone screen, a car windshield. Yet every one of them began as something you'd never expect, plain sand. But here's the real mystery. How does one of the world's most common materials become something perfectly transparent, incredibly strong, and precise enough to protect astronauts, skyscrapers, and the device in your pocket? The answer isn't just heat. It's one of the most astonishing industrial transformations ever engineered. By the end of this journey, you'll see why making glass isn't just about melting sand. It's a relentless battle against chemistry, gravity, extreme temperatures, and microscopic imperfections that can ruin an entire production line. You'll discover how factories transform mountains of raw materials into crystal-clear sheets, bottles, and precision. Engineered glass that must be flawless every single time. But that's only the beginning. Coming up, you'll find out why the sand used for glass isn't the same sand beneath your feet, why a furnace hotter than flowing lava has to run continuously for years without ever being turned off, and how a river of glowing liquid somehow becomes perfectly flat without anyone polishing its surface. Once you see what really happens inside a modern glass factory, you'll never look at an ordinary piece of glass the same way again. So, where does this incredible transformation actually begin? Not inside a blazing furnace, but with something so ordinary that most people walk over it without a second thought. Sand. Giant stockpiles of pale, almost white sand arrive at the factory every day, waiting to become one of the most useful materials on Earth. But here's the first surprise. Most sand can never become glass. The sand beneath your feet is usually packed with impurities, especially iron. Even tiny traces can turn perfectly clear glass into a green or brown tint. That's acceptable for some bottles, but it's completely unacceptable for windows, smartphone screens, or precision glass. So manufacturers use something very different. High silica sand, often containing more than 99% silicon dioxide. Every grain is chosen for one reason: purity. Because once the process begins, even the smallest contamination can affect the finished product. But sand alone isn't enough. Before anything reaches the furnace, massive computerized batching systems measure every ingredient with incredible precision. Alongside silica, two other minerals play critical roles. The first is soda ash. Pure silica melts at nearly 300 degrees Fahrenheit, hot enough to make large-scale manufacturing incredibly expensive. Soda ash lowers that melting temperature, allowing factories to produce glass far more efficiently. But solving one problem creates another. Glass made from only silica and soda ash would slowly dissolve in water. Imagine pouring yourself a drink, while the glass itself gradually disappeared. That's where limestone comes in. It stabilizes the chemical structure, giving glass the strength and durability we rely on every day. It's a simple ingredient, yet without it, modern glass wouldn't exist. Every batch follows an exact recipe. Even a tiny measuring error can create bubbles, weak spots, unwanted color, or internal stresses that may not appear until long after the glass leaves the factory. And once those materials enter the furnace, there's no easy way to correct a mistake. But perhaps the most surprising ingredient isn't mined at all. It's broken glass. Known as cullet, recycled glass is one of the most valuable materials in the entire process. Since it's already been melted once before, it softens much faster than raw minerals. That means less energy, lower fuel consumption, reduced emissions, and a more efficient production line. Before recycled glass can return to the furnace, though, it must be cleaned with remarkable precision. Powerful magnets remove steel. Eddy current systems separate aluminum. Optical scanners identify different colors at incredible speed, sorting clear, green, and amber glass into separate streams. Even tiny pieces of ceramic or stone are removed, because a defect almost too small to notice today could ruin an entire sheet of glass tomorrow. Inside this factory, perfection begins long before anything melts. Finally, after every ingredient has been weighed, inspected, and blended into a perfectly balanced mixture, conveyor systems carry the batch toward the heart of the factory. The temperature rises. The air begins to shimmer. And ahead waits one of the most extraordinary machines in modern manufacturing. A furnace so hot, it almost never turns off. Not overnight. Not on weekends. Sometimes, not for more than 10 years. That sounds impossible, until you discover why shutting it down is even more dangerous. If the molten glass inside were allowed to cool, thousands of tons of solidified material could trap equipment, damage the furnace, and force months of rebuilding before production could begin again. So the fire never stops. Inside, temperatures soar hotter than flowing lava. As the raw materials disappear into the glowing heat, every grain of sand begins losing its identity. Solid particles soften, chemicals react, trapped gases escape, and what started as dry mineral slowly transforms into a glowing river of molten glass. It looks mesmerizing, but appearances can be deceiving, because melting the ingredients is only the beginning. Hidden inside that glowing river is an almost invisible enemy capable of weakening an entire sheet of glass. Tiny bubbles. And removing them is one of the greatest engineering challenges in the entire factory. Those tiny bubbles might not seem important, until you realize that a single trapped bubble can weaken a sheet of glass, distort a window, or ruin a product worth thousands of dollars. As the molten glass moves through the furnace, the raw materials release gases that become trapped inside the glowing liquid. If those bubbles remain, the finished glass won't be perfectly clear, and for many products, that's simply unacceptable. So how do engineers remove something they can barely even see? The answer is patience and physics. Instead of rushing through the furnace, the molten glass flows slowly into refining zones where temperatures are carefully controlled. This gives the bubbles time to rise naturally to the surface and escape. Think of opening a bottle of sparkling water. The bubbles race upward because they're lighter than the liquid around them. The same principle works here, except instead of water, it's a glowing river hot enough to melt steel. Sometimes, refining agents help tiny bubbles combine into larger ones, allowing them to escape even faster. Throughout this process, sensors constantly monitor the furnace. Even a slight temperature change can alter how the molten glass flows. Too cool, and it becomes too thick. Too hot, and controlling it becomes far more difficult. Every adjustment has one purpose: to create a perfectly uniform stream of molten glass. Because what comes next changed the entire glass industry forever. For centuries, making flat glass was slow, expensive, and imperfect. Craftsmen blew giant cylinders, cut them open, flattened them by hand, then spent countless hours grinding and polishing the surface. The results were impressive, but never truly flawless. Everything changed when engineers asked a simple question: what if gravity could do the work instead? Their solution became one of the greatest breakthroughs in modern manufacturing. Freshly melted glass is poured onto a bath of molten tin. Not onto rollers. Not into a mold. Onto liquid metal. Why tin? Because molten tin is denser than glass. Instead of sinking, the glowing glass floats effortlessly across its surface. And something incredible happens. Gravity naturally pulls the top surface perfectly flat, while the liquid tin creates an equally smooth bottom surface. Without polishing. Without grinding. The factory produces an almost perfectly flat sheet of glass. It's one of those rare engineering solutions where nature does most of the work. The glowing ribbon stretches across the tin bath like a river of light. But despite its smooth appearance, it's still more than 1,800 degrees Fahrenheit. Cooling it too quickly would create invisible stresses trapped inside the glass. Cooling it unevenly would cause distortions. Even the atmosphere above the molten tin must be carefully controlled. Oxygen is kept away to prevent the tin from oxidizing and damaging the flawless surface below. Meanwhile, rollers along the edges gently control the ribbon's width and thickness. Need thin glass for picture frames? Adjust the rollers. Need thicker panels for large buildings? Adjust them again. The same production line can manufacture completely different products simply by controlling the flow. Eventually, the glowing ribbon leaves the molten tin, but it's still far from finished. Most people assume the glass simply cools until it becomes solid. In reality, that's exactly what engineers try to avoid. Rapid cooling locks invisible stresses inside the material, making it far more likely to crack later. Imagine taking a hot baking dish from the oven and plunging it into ice water. The sudden temperature change causes it to shatter. Glass behaves much the same way. So instead of rushing the process, the ribbon enters a massive temperature controlled tunnel known as the annealing layer. Here, the cooling happens slowly and with extraordinary precision. The temperature is lowered little by little, allowing the internal structure of the glass to relax naturally. This removes internal stresses and gives the finished product the strength needed for transportation and everyday use. It's one of the quietest stages in the factory, yet one of the most important. When the ribbon finally emerges, it looks completely ordinary. Clear. Smooth. Motionless. But appearances are deceiving. By this point, it has survived extreme heat, chemical reactions, bubble removal, floating across molten metal, and one of the most carefully controlled cooling processes in manufacturing. Surely it's finished now. Not even close. Before that glass can become a window, a skyscraper, or the screen you're looking through right now, it has one final challenge. It must prove it's absolutely perfect. And the technology used to inspect it can detect flaws so small, most people would never know they were there. Perhaps the most remarkable part isn't the technology alone. It's the incredible scale behind it. A modern float glass production line can manufacture hundreds of tons of glass every single day. That glowing ribbon you watched forming earlier never really stops. Hour after hour, day after day. It continues flowing through the factory, supplying everything from household windows and glass bottles to towering skyscrapers, vehicles, and advanced electronics used around the world. Yet despite all this automation, the process still depends on human expertise. Engineers monitor furnace temperatures, chemical composition, glass thickness, and production data around the clock. Operators make constant adjustments to keep the molten glass flowing perfectly, while maintenance teams inspect critical equipment before even the smallest issue can interrupt production. Because when a furnace operates continuously for years, there are no second chances. A small temperature change, a slight imbalance in the raw materials, or a tiny defect that escapes inspection can affect thousands of finished products. That's why every stage, from selecting high-purity sand to the final quality inspection, is controlled with extraordinary precision. And that's the real secret behind every glass you've ever touched. It isn't just sand. It isn't just heat. It's the perfect combination of chemistry, physics, advanced machinery, and human expertise working together to transform one of Earth's most common materials into something so flawless, we rarely stop to appreciate it. From a handful of ordinary grains to the crystal-clear glass protecting our homes, cars, phones, and cities, every step has one purpose: to create perfection from something completely ordinary. The next time you hold a drinking glass, look through a window or unlock your phone, remember. You're not looking at just glass. You're looking at ordinary sand transformed by extraordinary engineering. From carefully selected minerals in furnaces hotter than lava to molten tin, precision cooling, and microscopic inspections, every step is designed to create something so perfect, you rarely stop to appreciate it. And that's the real secret behind every glass you've ever touched. It isn't the sand that makes it remarkable. It's the incredible engineering that transforms it. If you enjoy discovering the hidden world behind everyday objects, consider subscribing for more factory stories that reveal how the things we use every day are really made. Until next time, keep looking closer, because ordinary things often hide extraordinary secrets.